All right, let's begin. Today, we're turning our attention to a really fascinating subject of astronomical interest, the constellation Camelopardalis. We're going to be exploring the paradox that it represents. You see, this is a huge area of the sky, but to our own eyes, it's almost completely empty. Now, this isn't just a simple curiosity. It's actually a gateway to understanding some fundamental concepts, from stellar magnitude all the way to galactic structure and even observational cosmology.
So this is the central question that's going to guide our investigation. How can the 18th largest constellation in the entire sky be practically invisible? By every official measure, it's enormous, and yet its stars are so dim that it just looks like a vacuum. Our goal today is to really dissect this apparent contradiction. And what you'll find is that its emptiness is actually its greatest feature, giving us an incredibly clear line of sight deep into the universe.
So here's our roadmap for today's discussion. First, we'll map out this invisible giant, looking at its astrometric profile. Second, we'll delve into its history, a beast of many names. Third, and this is the really exciting part, we'll explore its astrophysical deep field. Fourth, we'll touch on its more modern symbolic meaning. And finally, we'll wrap up with a practical guide for how you can find it yourself.
Okay, Section 1, Mapping the Invisible Giant. Here, we're going to establish the basic data, the fundamental measurements that define this constellation's position and, more importantly, its scale up there on the celestial sphere.
Let's start with its sheer size. The official area of Camelopardalis is 756.8 square degrees. Now, to put that in perspective, that makes it the 18th largest of all 88 constellations. It's bigger than famous ones like Orion or Gemini. So the problem we're dealing with here isn't one of scale, it's one of luminosity.
Now, a really key characteristic is its circumpolar nature, at least for observers in high northern latitudes. If you're anywhere above 45 degrees north, this constellation will never set. It never dips below the horizon. I want you to picture the night sky pivoting around Polaris, the North Star. Camelopardalis is so close to that celestial pole that its entire nightly path stays above your horizon, making it a constant, year-round feature of the sky.
And this table really lays out how its visibility changes depending on where you are on Earth. That circumpolar status for the north transitions to seasonal visibility as you move south towards the equator. Then, once you get into the southern hemisphere, say between 10 and 37 degrees south, it barely scrapes above the northern horizon. And if you go any further south than that, it's permanently below the horizon. You'll never see.
All right, Section 2, a beast of many names. You see, unlike the classical constellations from Ptolemy's time, Camelopardalis is a modern invention. It was born out of the mapping challenges of the late 16th century, so its history isn't one of ancient mythology, but one of naming and map-making.
So, let's go back to 1598. A Flemish cartographer named Petrus Plancius was looking at this large, empty patch of sky between the well-known shapes of Ursa Major and Cassiopeia. He decided to fill it. His first idea was actually biblical. He named it for the camel that Rebekah rode to meet Isaac. But the name he chose, Camelopardalis, is pure Greek. It literally means camel leopard, which was the classical term for a giraffe. And it was that giraffe interpretation that stuck, thanks to Jacob Bartsch's star atlas in 1624, which clearly depicted it as a giraffe.
Okay, now we get to the heart of our analysis. The very thing that makes Camelopardalis seem empty, the low density of bright stars and dust in our own galaxy in that direction, is exactly what makes it such a special, clear window into extragalactic space. This apparent void is, in reality, a treasure trove for deep sky observation.
First, let's consider the star Alpha Camelopardalis. This is a blue supergiant, an incredibly massive and luminous star. Just look at the comparison here. It's about 30 times the mass of our Sun and an astounding 500,000 times more luminous. But what's really remarkable is its speed. It's moving at over 60 kilometers per second relative to its neighbors. This thing is a runaway star.
So the question is, how does a star get ejected like that? Well, the accepted theory involves a powerful event in its home star cluster. There are two main possibilities. One is the binary supernova scenario. Alpha Cam had a massive partner star, and when that partner exploded as a supernova, the blast and sudden loss of gravity kicked Alpha Cam out into space. The other possibility is a close gravitational encounter with another massive system, basically a gravitational slingshot that flung it away.
Now, to understand our next object, we need a quick primer on something called an HII region. Think of these as cosmic star factories. They're vast clouds of hydrogen gas that are being lit up from within by the intense radiation of hot, young stars.
This energy ionizes the hydrogen, and when the electrons and protons recombine, they emit light at very specific wavelengths, especially this prominent red light called H-alpha. So when you see this red glow, you're looking at active star birth.
With that in mind, let's turn our attention to the spiral galaxy NGC 2403. It's about 8 million light-years away, which is relatively close for a galaxy. And when we look at images of it, we can clearly see its spiral arms are dotted with these distinct, glowing knots of red light. Those are the H2 regions we just talked about. Seeing so many of them tells us that this is a very active galaxy, with a high rate of ongoing star formation.
Okay, let's come back into our own galaxy for a moment and look at something just visually stunning. This is Kemble's Cascade. Now, it's crucial to understand this is an asterism, not a true star cluster. It's a line-of-sight illusion. We're seeing over 20 stars that just happen to line up perfectly from our perspective, but they aren't physically related. This beautiful chain stretches for about 2.5 degrees, which is the width of 5 full moons side by side. It's a spectacular geometric coincidence.
Now for this number, 13.3 billion years. Just take a moment to absorb that. This is the time it has taken for light to travel to us from a galaxy known as MAX 0647 JD. This is one of the most distant objects we have ever seen, right at the very edge of what's possible for observational cosmology.
This is a perfect example of what we call cosmic archaeology. Because light has a finite speed, looking at something incredibly far away is the same as looking back in time. The light from MAX 0647 JD that hits our telescopes today started its journey when the universe was only 420 million years old. This lets us directly study what galaxies looked like and how they behaved in the infancy of the cosmos. All right, let's shift gears for a moment. As a brief addition to our scientific analysis, let's talk about the symbolic meaning that people have given to this constellation, especially since it doesn't have any ancient myths of its own. Modern stargazers often see it as a silent observer. Its long neck appears to be stretching up towards the north celestial pole, as if it's trying to see beyond the obvious. Its faintness has also been seen as a symbol of humility, which connects back to Plancius's original biblical idea. And from a scientific perspective, it's become a symbol for the search for knowledge itself. This idea that the greatest truths often aren't bright and obvious, but require patience and effort to uncover.
And that brings us to our final section, a practical guide. Let's talk about how you can actually go out and find this seemingly invisible giant for yourself. It's a great exercise in observational skill.
Okay, step 1 is non-negotiable. You need a dark sky, far from city lights. Then you're going to use a technique called star hopping. You find bright, easy-to-spot markers like Polaris, the brilliant star Capella, the Big Dipper, and Cassiopeia. The vast, seemingly empty region bounded by all of these bright markers, that is where you'll find Camelopardalis. You're not looking for a distinct shape, but rather using averted vision to pick out the faint stars scattered within that area.
So what equipment do you need? A simple pair of binoculars is perfect for sweeping this area. They have a wide field of view that is absolutely ideal for taking in the full length of Kemble's Cascade. But if you want to see the spiral arms and those HII regions in the galaxy NGC 2403, you're going to need more power. A telescope with an aperture of 150 millimeters, that's 6 inches or larger, is really what's required.
This quote really sums up the whole point perfectly. It says, Camelopardalis is a constellation test. It teaches us to see beauty where at first glance there is nothing. It really is a test of an observer's skill, and it reinforces a core idea in science. Discovery isn't always about looking at the brightest, loudest things. It's often about the careful, patient examination of the things that seem unremarkable.
And so we'll end with this question for you to think about. In a universe that we often define by its most violent and energetic events, things like quasars and supernovae, what profound secrets might be hiding in the vast, quiet, silent regions of space? Studying these apparently empty fields, just like the one offered by Camelopardalis, might just prove to be as scientifically important as studying the brightest objects in our sky.